we'll start with the first one here. A quick look at it. I see nothing squared, so I don't think about starting to use one of my Pythagorean identities. I see cotangent, tangent on one side, cosecant, secant on the other. So I have a bunch of different functions. So my first thought would be, let's change things to sine and cos and just get a single fraction on both sides to see what happens. So here I'm going to have cos theta over sine theta plus sine theta over cos theta. Oops, no equal sign there. And on this side I'd have 1 over sine theta times by 1 over cos theta. Multiplying fractions, you multiply the tops, you multiply the bottoms. So this one, right away, I have a single fraction on the right-hand side. On the other side, I'm adding fractions. In order to add fractions, I need a common denominator. So the work that you would show is in this first one, I'd have to multiply the top and bottom by cos theta. In the second one, I'd have to multiply the top and bottom by sine theta to get my common denominator. So now I have a common denominator of sine theta cos theta. And you can write that on the bottom of your fraction right away, because now you can just add the tops. And on the top, I'm going to get cos squared plus sine squared. And then we recognize we have a squared, so we look at our identities that are our Pythagorean identities, and of course cos squared plus sine squared is equal to 1. So we are done. The left side is equal to the right side. Awesome. So there's part A. For part B, so looking at this one, I see cotangent and I see cosecant. I also see that the cosecant is squared. So thinking of that, I know that there's a relationship between cotangent and cosecant, because cotangent squared theta plus 1 is equal to cosecant squared. So one way that I could go about this one right away is where the cosecant squared is, instead of writing cosecant squared, I could write cotangent squared theta plus 1, because they're equal to each other. And now if you distribute this, you're going to get cotangent cubed theta plus cotangent theta minus cotangent theta. And of course, these are like terms. They'll cancel out, and we just get cotangent cubed. And so our left side's equal to our right side, and we are done. So that is one way that you could go about solving for that one. And that would be better than changing everything to sine and cos. Sine and cos will work, it just takes longer. Okay? Now I'm going to do this same proof again with a tiny little different strategy that's also fairly quick. So for this one, I'm going to erase this up. Again, it's still based on the idea that I'm going to look at cosecant and cotangent because I know they're related. But on this one, I see that I have two terms that have a cotangent in common. So I'm going to use the factoring strategy. I'm going to factor out a cotangent and see what I have left. That will leave me with cosecant squared theta minus 1, taking that cotangent out of each of them. If I do that, again, my cosecant squared minus 1, you can look at these Pythagorean identities, and if in one step you could get cosecant squared minus 1 just by looking at that equation, can you see if you move the 1 over to the other side? Cosecant squared minus 1 is cotangent squared. So you wouldn't have to show more work than that. Because if you can do that in one step just looking at the proofs, it's okay to just plug that in. So because cosecant squared minus 1 is cotangent squared, you can substitute that in. Of course, this times this becomes cotangent cubed theta. I'm going to add a part C to this one, which you can try to prove under that think further at the bottom of the page. Okay. Do you want it medium level or difficult level? Medium level. Okay. Okay. The left-hand side is going to be tan to the power 4 minus secant to the power 4 theta. This is what we want to prove. This is medium. And negative tan squared theta minus secant squared theta. Okay? That would be on the right-hand side. If I wanted to make it a difficult one, I would have made it equal to negative sine squared theta minus 1 over cos squared theta. So this is optional. Once you've proven the first part, if you want to keep going and prove the second part, you could. It's not that. This middle part as a hint actually makes the whole thing a little bit easier. Yeah. Okay, so I will just split it right here. We will do the medium one. Currently, right at the beginning, they are, the left side, you could think of this, I'll just make this go away. This is over 1, and this is over 1. So technically, they're both single fractions because the denominator would be over 1 at this point. And so they're not the same. And if we go back to our strategies, another thing we look at, we see tan and secant, and that might be a good thing to keep them as tan and secant because there's a relationship between tan and secant. So it seems to be like maybe it's a good idea to keep them together that way instead of changing to sine and cos. This is one where if we do change it to sine and cos, especially with those powers of 4, it could get really messy. So technically, we're stuck. So when we get stuck, we either try to build the other side or we try to factor. And if we're going to try to factor, we're going to see, is there any difference of squares in this question? Can you see that the right side is a difference, the left side is a difference of squared. This is something squared minus something else squared. The right side has 2 things squared, but there's an extra minus out in front, which kind of ruins things for making it a difference of squared. So if I go to the left side here, and I set up my brackets to factor it, well, what times what is tan to the 4? Tan squared, oh, I'm still using the thing that erases. That's not good. Have to rewrite it. There we go. Tan squared and tan squared makes tan to the 4. Secant squared and secant squared makes secant to the 4. And one of these will be positive and one of them will be negative. Of these two, if you look at your tan squared plus 1 equals secant squared, and I'll write it over here temporarily. Tan squared plus 1 equals secant squared. Can you see that you could get tan squared minus secant squared in that equation by moving the secant squared to this side? That would give me tan squared to secant squared. But then I'd have to get rid of this 1 on that side by moving it over to that side. So what's tan squared minus secant squared equal to? A negative 1. And then when I distribute that negative 1, I'm going to get negative tan squared minus secant squared. And we're done. The reason the stuff in the dotted box would make the question a lot harder is probably when you see this side with sine and cos already, you would have been tempted to change this side to sine and cos first. And then it would be hard. But having this, tan squared is sine squared over cos squared, and secant is 1 over cos squared. You'd already have a common denominator at that point. And then when you subtract the tops, you would get negative sine squared theta minus 1 all over cos squared theta. Okay, the ones that you can do in your homework after question example 1 are 3, 5, 6, I, 7, I, and 9, I.